Hello and welcome to part 3 of the review of the periodic table. So the main goal of the periodic table, or the main goal that scientists has, was to organize the elements meaningfully. The first attempt was to organize elements in terms of properties, and that's understandable. However, with many of the first attempts, the problem was that everyone organized them differently. And of course the problem with that is that communication was stifled. People just couldn't communicate with each other clearly. So one of the first scientists that tried to organize the elements meaningfully was John Dalton, and he used symbols to organize the elements. So that's what he did. A later contributor decided to, instead of, so Berzelius decided that a better way to organize the elements was to use letters instead of symbols, and that's very good because it allowed people to communicate clearly without any problems. So for example, hydrogen has the capital letter H. Now helium also starts with an H, but because there's already an element that starts with the letter H, we have to adopt the second letter in the word and attach it to the symbol using the lowercase letter. So helium, is represented by HE. Okay. Carbon is another really good example. Carbon is represented by the symbol C, and just to hit the point home here, another element that could be represented with C but isn't is calcium. So adopting Berzelius's rules here, we take the capital letter C, and because carbon already exists there with its own capital letter, we have to take the second letter and use the lowercase version of it. And the slide just represents what I said earlier. Of course, a lot of these symbols here don't really make any sense if you're thinking about them in terms of English. However, the problem with it is that it doesn't matter what language you're using, it would be very, very difficult to communicate across languages. So what scientists decided to do is they decided to use one common language so that everyone would understand what the symbols mean, and that language was Latin. Okay, so whenever you're looking at the periodic table and trying to find gold, and you look at it and go, well, that's kind of weird, gold is represented by AU, and lead, which is spelled LE80, is represented with capital letter P next to small letter B. Well, that's because they're using the Latin names to name these two elements. So elements were soon organized by atomic mass, and the atomic mass is found on the periodic table, and it is measured in units called atomic mass units. And what an atomic mass unit is, it is the mass of one atom of one element. Okay, so what does that mean? So atomic mass unit, let's say we take this chunk here of fluorine, okay? And let's imagine that we can chop it up many times, over and over and over again. So we chop it up, we keep chopping it up, and then we find that we break it down so many times that we get the element of fluorine. Okay, so let's take the element of fluorine and further chop that up over and over and over and over again. And then we find that when we break down the element, we get an atom of fluorine. Okay, one of those atoms has a mass that's measured in AMUs. Every element has different atoms with different masses. So an atom of carbon is going to have a different mass than an atom of fluorine. So now I think it's a really good time to go ahead and show you how to draw a Bohr model of the diagram. For my students that happen to be watching this in order to review, you're going to have to be able to do these. Okay, so I've chosen fluorine as an example, just because we talked about it in the last slide. Alright, so the first thing you need to do is when you're doing Bohr models is you need to go ahead and look at your periodic table. And you need to find the atomic number. So this is a place where some students make mistakes. This is your atomic number up here. This is your atomic mass. They are different things. The atomic number is going to tell you the number of protons and the number of electrons. Okay? Because we're assuming that the atom is stable, so if it's stable, that means the number of protons usually is equal to the number of electrons. So that is our atomic number. So we're going to go ahead and we are going to write up here in our corner the number of protons and electrons. So we have number of protons, we've got 9. Number of electrons, oops, that should only be, I gotta fix that. Okay, number of electrons we have is also equal to 9. Alright, so here's a point where a lot of people can make mistakes, okay, because we need to find out what the number of neutrons are, and we also need to figure out how to do that. So how are we going to figure this out? Okay, we don't have a number directly telling us to. So this is how you do it. If you think about it, the atom is made up of 3 subatomic particles. It's made up of the protons, the electrons, and the neutrons. So the total mass then is equal to the mass of the protons plus the mass of the electrons plus the mass of the neutrons. But in reality, the mass of the electron is very, 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 very small compared to the mass of the proton and the mass of the neutron. So what a lot of people do, and for our purposes, we just ignore the mass of the electron. It doesn't contribute a lot to the overall atomic mass, so we ignore it. So here's the formula that you're going to need to use to find the number of neutrons. So first thing you do is you take your atomic mass, okay, and you subtract it by the number of protons. So number of protons, and that will give you the number of neutrons. Well, that is not a negative sign, force of habit, number of neutrons. Okay, usually you could do this. You can do neutron positive / negative, indicating that it's neutral. Okay, so our atomic mass. Again, atomic mass, this is not our atomic mass. We need to find our atomic mass, which is there. Okay, our atomic mass, we're just going to round it up, is 19. We're going to subtract by a number of protons, which is 9, and that is equal to 10. So there you go. This is a very good example where a lot of people who think that the number of neutrons are simply going to be equal to the number of protons and the number of electrons, that is not always the case for every single atom, and that is why fluorine is a pretty good example to talk about. So now we are ready. We have all the information we have. We're ready to go ahead and draw our Bohr diagram. First step is to draw our nucleus, which is right in the middle. So that's not too bad. Here we have a nice circle representing our nucleus, and we find protons and neutrons located in the nucleus, so we're going to draw those there. So we got 9. Oops. Okay, we've got 9. Why is this not working? 9 protons, and we've got 10 neutrons. Okay, so that's not very clear, but you get the picture. Alright, so then now we're going to go ahead and we're going to draw our first valence shell. And in our first valence shell we have 2 electrons. So we're going to draw 2 electrons. I have a hard time drawing circles here, so I'm just going to use X's to represent our electrons. Okay. Now we're going to draw our next orbital, or our next valence shell. Okay. And on our next valence shell we have a maximum number of 8 electrons that we can put. Okay, so since we took 2 electrons to put in our first valence shell, 9 minus 2 is equal to 7. So we have a total of 7 electrons that need to be distributed, so we're nice. We're under the valence shell total maximum number of electrons, so we know that we're not going to need any more valence shells. So fluorine is just going to have 2 valence shells. Also, it is in the second period, so that reflects the number of valence shells that you're going to have. Okay, so that's another periodic trend for you. Okay. The number of the periods reflects the number of valence shells that you're going to see when you're drawing atomic models. Okay, so electrons like to pair up, so we're going to go ahead and draw the electrons. Okay, so we got 1, 2, 3, 4, 5, 6, and then we've got our lone electron 7. And there's the Bohr model for fluorine. So let's see if we got it correct. I pulled this image from the internet. So let's see if we got it correct here. Oops. And it looks like we did a pretty good job. Okay. So again, here's the Bohr model for fluorine. 9 protons, 10 neutrons, 2 electrons, maximum amount to the first valence shell, and then we have the rest of the electrons, 7 electrons on the outer second shell of fluorine, which totals to 9 total electrons. Dmitry Mendeleev, this is a familiar name. This is a name you need to be familiar with, and he is the individual that invented the periodic table. So he organized the elements and reflected patterns in their properties. So he didn't just put the elements on the periodic table in any old fashion. He did them. He ordered them in such a way that it reflected the properties. Okay. So he wanted to find a pattern that would allow him to predict the properties of elements yet to be discovered. So if there's anything that was missing, if there's any missing gaps in the periodic table, he organized it in such a way that he was able to predict the properties of any missing gaps. Okay, these gaps would be later filled in by newly discovered elements that have an atomic mass and properties needed to fill in a particular spot. Newly discovered elements have never been done since Mendeleev first put it together, which is why the year 2016 was pretty significant, because the scientists managed to fill in those gaps on the periodic table and name them. So you'll see different versions of the periodic table. Here's an example of the old periodic table. It's seemingly complete. However, if you look very closely, you see over here there's an empty space, right? And these are gaps that are in the periodic table. Okay, but for example, in this group or family right here, we know that it's very reactive. Fluorine is quite reactive. Chlorine, bromine, iodine, and astatine are all quite reactive. And so we would guess that because this block here falls in that same family or group, that this element here would also be just as reactive. And newer periodic tables look like this. So this is the complete periodic table, right? And these elements here have been given names quite recently. So the periodic table reflects organizations of properties, so we're going to look at some periodic trends. Okay, so this is generally what the periodic table is going to look like. The periodic table is broken up into 3 main parts: nonmetals, metals, and metalloids. Okay, so again, there's the periodic table. Periodic table here. Okay, so the first thing I'd like to draw your attention to is this part, the rightmost part of the periodic table. If you look at it quite closely, and I'll try to highlight this for you here. I'll try this. Let's see what this is going to look like. I don't know. No, it's not going to work. So this part here, if you can see that, or you just kind of follow where I'm going with this. This part of the periodic table is called the staircase. Okay, and the staircase has one important thing. It separates the metals from the nonmetals. Okay, the metals are going to be found anywhere left of the left of the staircase on the periodic table, and metals are going to be found. Nonmetals are going to be found on the right side of the periodic table. Okay, so let me repeat that just in case I kind of mix things up. Excuse me. Nonmetals are going to be on the right side of the staircase, and metals are going to be on the left side of the staircase. So if we have metals on the left and nonmetals on the right, then it makes sense that this junction here is kind of special, because this is the junction at which, metals start to become or if you're going from this part of the periodic table, things become more non-metallic. If you go from this part of the periodic table to this part, to the left side, then things start to become more metallic. So there is this junction here where there are some elements that are kind of metals and kind of not metals. So they're pretty interesting. Okay, so again, as you go from left to right on the table, the elements become less metallic. As you go right to left, the elements get more metallic. Okay, so those are two periodic trends. Okay, so metalloids are elements that have both metal and non-metal properties, and they're highlighted here in red. Okay, so some of these metalloids are semiconductors, and all that means is that sometimes they carry electrical charge and sometimes they don't. They carry electrical charge under special circumstances, which is why they're used in computers. Okay. Okay, so non-metals. Okay, so everything here highlighted in blue are non-metals. Okay, they're to the right of the staircase. They're usually solids or gases at room temperature. Bromine is the only exception. It's a liquid. They are insulators. They are not very ductile or malleable, and they're found in groups 14 to 16. You are responsible for knowing, make sure that you know, the properties of nonmetals. Okay, and they're listed here for you. They're usually solids or gases except bromine. They're insulators, and they're not very ductile or malleable. The other thing I want to point out to you is hydrogen is right here. Hydrogen can be found here on some periodic tables or in the middle in other periodic tables. Hydrogen is not an alkali metal. Okay, this group here is called the alkali metals. Hydrogen is not an alkali metal. Hydrogen is considered to be a non-metal. It's a gas. Metals. So metals are shown in tan color. Okay, so again, this is the third part of the periodic table. Here we have the metalloids, and then we have over here in blue we have the non-metals, and now we have all the rest of the periodic table, which are metals. Metals are shiny, they're malleable and ductile. Okay, whereas non-metals are typically dull, not very malleable and not very ductile. They conduct electricity and heat, okay, whereas nonmetals are insulators, and they are all solid at room temperature except for mercury. Okay, don't get confused with gallium. Gallium is a solid at room temperature, but that's if you heat it up just slightly, like so, if you put it in your hand, for example, it'll start to melt. It's not a liquid at room temperature, though. Major groups of the periodic table, we're going to talk about these. The alkali metals are group 1, alkaline earth metals are group 2, halogens are group 17, and the noble gases are group 18. And they're grouped together in similar families because they have similar physical and chemical properties. So group 1 right here, okay, not very good at drawing the arrows, but those are the alkali metals. They are the most reactive of all the metals, and notice that the most reactive metals are on the leftmost side of the periodic table. Okay? As you go down the group, the reactivity is going to increase. Okay, so francium, which is, I can't remember right now, I do believe it's at the bottom here, is more reactive than, let's say, sodium or lithium. Okay? Again, it does not include hydrogen. They are quite reactive with water. Some of them are so reactive with water that they will react spontaneously with the water vapor in the air. And because of that, they require special storage. They like to donate electrons when forming an ionic compound. Alkaline earth metals in group 2. They're also quite reactive, but they are just one family, one group further to the right. So they are quite reactive, but they're not as reactive as the alkali metals. So the alkaline earth metals, donate 2 electrons when forming ionic compounds. And examples of the alkaline earth metals could be calcium, okay, for example. Calcium, potassium are 2 examples. The halogens, now we're skipping all this part here. These are called the transition metals, but we're skipping those for now, and we're going right here to this group, which is group 17. So this is group 17. I'll try drawing a 17 for you. Group 17. My pen disappeared. Oh, here it is. 17 right here. Okay, and these are called the halogens. They are all non-metals. They are the most reactive of all the non-metals on the right part of the staircase. Again, notice that they're at the periphery. In other words, the furthest most edge of the periodic table almost, okay? And they're quite reactive. They each exist in different states of matter at room temperature, so some of them are gases, some of them are liquids. There's no real pattern to them. Compounds that have halogens in them are called salts. Salts are usually formed when a halogen combines with an alkali metal. You can also say that compounds that have alkali metals in them, for the most part, they're usually salts. Examples of halogens include fluorine and chlorine. The noble gases, okay, this is group number, where's my pen? This is group 18, okay? And they are on the furthest rightmost part of the periodic table. Now, these 2 groups here, group 1 and group 2, are quite reactive, as well as group 17. This is where things differ a little bit, because the noble gases are not reactive. Okay? They are also called inert gases because they don't react with things. They have a full outer valence shell of electrons. This makes them quite stable. So, for example, helium. Okay, if we draw helium, which is quite simple, I'm just going to just draw helium like this. Oh, my pen's not working, not cooperating right now. There's our nucleus, and then we have our 1 valence shell, which has a maximum of 2 electrons, and helium, having the atomic number of 2, has 2 electrons, and that is a full valence shell. And all of these atomic models here, group 18, are also going to have the same configuration, where they have a total number of the full valence electrons. In other words, so for example, in this group here, this element will have 8 full valence electrons in the second shell. Okay, and that's why they're very stable. So if you're asked the question, why is it that noble gases are stable? It's because they have a full outer valence shell, and it occupies the most amount of electrons possible. So a couple of periodic trends for you before we're almost done here. Atomic mass, as you go left to right in a period, the atomic mass increases. As you go down a family or group, the atomic mass increases. Atomic number, as you go left to right in a period, the atomic number increases. As you go down a family or group, the atomic number increases. Reactivity, as you go down a group, reactivity increases. As you go up a group, reactivity decreases. And the atomic radii, which is just has to do with the size. The radius of an atom increases as you go down the periodic table and as you go left on the periodic table. So this one's a little bit not very predictable, okay, just because of this last part here. This is just a review on how you guys should be looking at the periodic table. So some information you'll find there. You find the element name. You find the atomic number, which tells you the number of protons in the nucleus of the atom. If the atom is stable, that is also the number of electrons. It is not always the number of neutrons. Again, to calculate the number of neutrons, you take the atomic mass, which is shown to you right there, 12.01, which is the average mass of the atoms in an element, measured in AMU. Okay, and you take that and you subtract it by the number of protons, or the atomic number, and you get the number of neutrons. And here you have the symbol. Okay, I hope that was very helpful, and I know this was a longer video, but hopefully it was worth it. Have a good day.